The overall goal of the following experiment is to apply tensile force to the axonal process of a neuron in order to stimulate and sustain its growth. This is achieved by plating neurons within a computer-controlled bioreactor upon a micro-manipulated towing substrate. After plating, neurons are cultured up to 1 week, during which axons extend onto a stationary substrate via growth cone extension. Next, axon stretch growth is performed by towing the plated cell bodies away from the axon terminals adhered to the stationary substrate. The tissue engineering technique of axon stretch growth is capable of sustained growth rates up to 10 mm per day, resulting in long fascicular bundles of enlarged axon tracts based on microscopic analysis.
The main advantage of this technique over other methods like growth cone extension is that axon stretch growth allows the experimenter to grow fascicular axon tracts to any desired length in shorter time periods.
The implications of axon stretch growth are that it allows us to recreate the biomechanical signals that stimulate nerve growth. These signals can be studied in order to exploit them and develop new strategies to treat diseased or injured nerves.
So the axon stretch growth method can help answer key fundamental questions about the development and maintenance of the nervous system. Importantly, we can explore the mechanisms that allow axons to grow at rates faster than we thought possible.
The axon stretch growth bioreactor system has 3 main components. First, a bioreactor chamber where neurons are cultured and stretched. Second, an automated linear motion table which applies stretching forces. And lastly, a step